Okay, first some talk on whatever it was. You've had two tests out there right now, I think, that you can take if you want to. One of them is due this Wednesday midnight, the other one's due this Friday midnight, I believe. And today I'm going to put up the test for everybody, which is the test on chapter 10. And that will be due Monday at midnight, okay? So about that is real quickly, what's in that section, what's in that chapter, and I'm not just going through my notes here, I'm just doing some memory. I believe that had to do with describing curves with representations with like an X and a Y. So parametric representations and arc lengths. Is that right? Okay, parametrically. We had arc length already, but this is a little different. And then there was polar stuff and polar graphs, and then there were conic sections. That's all that stuff, okay? So you can expect to have something like a polar graph. You can expect to have things about conics, to recognize a hyperbola or develop the equation of a hyperbola or parabola, that sort of stuff. We had also an area of a curve described in parametrically, and we had surface area described parametrically, I believe. And so I'm just off the top of my head thinking of some things that will probably be problems on the test. Okay? So we'll talk more about that. Maybe Wednesday, maybe I'll talk a little more about that. You guys don't seem to be in a hurry to take tests. So maybe if I talk a little bit more about the test on Wednesday, some of you won't have started it yet. Anyway, what we ended up on, well, I think Friday, was alternating series. And we write an alternating series differently than we write all the other series, in the sense that most series we write with a K or an N, and we most of the time start at 1. We might start someplace else, but most of the time we start A sub 1, A sub 2. And you know we have partial sums. All right, that's why I like to use N and K here. Partial sums are the same looking thing, except they stop at N. And so we talk about the limit of the sequence of partial sums. This is a review, and that's the sum, called the sum of the series. And if this exists, then we go and we say the series adds up to that, even though that's not how we find it. We take a limit, we don't take a sum. Okay. The idea usually is to convert the partial sums into something we can take a limit of. That's how we do. Now remember, when we did all this, all the terms were positive. That's how we just talked about it to start with. Okay. Well, if we now go to half of them are negative and half of them are positive, the way to do that is to make the index, again, it's going to be 1 to infinity probably. And if I do now what I just wrote, if I translated this one, this would be -1 plus 1 minus 1 plus 1. No, it's all addition. It'd be -1 plus 1 plus -1 plus 1, technically, because it's still summing. It's just you're summing half of them negative. And if we look at the partial sums of this one, the S1 would be A1, that would be -1. S2 would be the sum of the first two, that would be 0. S3 would be the sum of the first three, that would be -1. S4 would be the sum of the first 4, that would be 0. And you should be able to see that this series diverges. Okay? Because the sequence of partial sums does not have a limit. The sequence of partial sums has two limiting points. Remember we talked about when you don't have a limit, where you might have two things to go to or three. This is a sequence that has two limiting points. You only have the limit of a sequence exists if there's only one limiting point, namely called a limit. In this case, since half of them are 0 and half of them are -1, there's no limit of the sequence of partial sums, and therefore the series diverges. That's what we say. Now, if I change this to k plus 1 or to k minus 1, either one, I don't like doing it to k minus 1 because the first term then becomes -1 to the 0 power, which is okay, it becomes 1, but I'd rather personally not have that problem because that's a problem in notation, not in terms of anything else. So if I put in 1, I'll get 2 up here. -1 squared is +1. So if I use k plus 1 instead of k as the power, then what I've done is changed all of the partial sums. Now the partial sums are 1, 0, 1, 0. Still doesn't exist. I've changed what the partial sums are, but not the fact they don't have a limit. Okay? But this is an alternating series. Now, how do we write an alternating series? Well, if I write it this way, like this, and I say half of them are minus, the trouble is you can't see the minus. Okay? I can say the even ones are plus and the odd ones are minus. I can write that over here someplace. But the notation doesn't show you any minuses. And as humanly, because we start out with this stuff, when you see this, you just automatically think they're all positive. I mean, hopefully you think about stuff when you look at it. But if you don't think about stuff when you look at it, you'll go back to what you learn most, which is when they're all positive. So we don't write an alternating series this way. Most of the time, we write it with a -1 in it and maybe a BK instead of an AK, where all the BKs are positive. Okay, for all K, the BKs are positive. And so now, if we want to start out minus B1, we will put K. If we want to start out plus, we will put K plus 1 or K minus 1. So this series, what I've just written says B1 minus B2 plus B3 minus B4, and so on. And it's called alternating, and it's the only place. The terms here are not the terms of this. So now, you'll be given a series BKs. I'm sorry. You'll be given a sequence. Some people want in. Oh, wait. Admit, don't remove. Dalton wants in. Dalton, sorry, I didn't see you there. So Dalton has now joined us. Dalton must maybe look at the video tonight or something, or tomorrow, whenever it comes around. Anyway, the actual terms of this series involve the -1, but we kind of talk about the terms being the things besides the -1, if you see what I'm saying. Okay, so in section 11.5, it's on page 772, you will see the description of these things involves the B's, not the -1 B's. I mean, it involves only the B's. And what it says on the bottom of page 772, and by the way, you'll notice that the author uses K minus 1. I tried to explain to you a couple times why I use K plus 1. I don't like to have 0 in an exponent because that's just a mistaken notation. So why complicate things? But in any event, the book says if the B's are non-increasing, what in the world does that mean? That means as the thing gets bigger. So B sub, he writes N, plus 1 and Bn. If these things were increasing, then this would be bigger than this. If they are decreasing, this would be smaller than this. The 51st one will be smaller than the 50th if they're decreasing. So what I want to put here is less than. So the terms, now, the terms are actually the A's, but people say the terms with the B's is saying without the minuses. If these things are getting smaller, yeah, and if the limit of them is 0, those are the two conditions. It says the series is convergent. So this is, alternating series are relatively easy. In other words, if I take this series, 1 to infinity minus 1, k minus 1 or plus 1, either one, and write k here, you know the series diverges. Why? Because the bk's are getting bigger. Okay? Now, if I write 1 over k, now the bk's are getting smaller. And their limit, not the series, but the limit of the thing goes to 0. Limit of 1 over k is k goes to 0. So this series converges. It's called the alternating harmonic series. And it's the easiest example of a convergent alternating series. Now, what if I put 1 over k squared? 1 over k squared, are those numbers getting small as k gets big? Yes. Or do they go, there's a limit of 1 over k squared, 0? Yes. So 1 over k squared, alternating series, converges. What about 1 over the square root of k? It converges if it's alternating. Now, something we're going to learn about is when I have a series of AKs and I have a series of absolute AKs. Sorry about my space. Two different series here, okay? Well, these two are identical if all the A's are positive. Then it's the same series. So we could have started out by talking about absolute AK over here instead of AK, because that's the same thing if A's are positive. Now, if I have a series and I don't know whether the terms are positive, I just have a series, a bunch of things added together. This series is called the absolute value series of the original series. So the absolute value series is a series you construct by putting absolute values around the terms of the original series. That doesn't change anything if all the original terms are positive. If all the original terms are negative, it changes all of them. Okay? But we could have handled that already. If all of them are negative, you take the minus out, then all of them are positive, and you see whether the positive ones go and you put a minus on the end. Does that make sense? Okay, so we do that. Now, if some of the A's are negative, suppose the first 10 are negative, the next 10 are positive, the next 10 are negative, and so on. Suppose every 10 are negative, and it alternates. That's not an alternating series. The absolute value series will be all the ones with just pluses. You get rid of all the minuses. Now, we're going to prove later that if this series converges, then this series will converge. If the ones without any minuses converges, then the other one converges. It's an if-then sentence. It's conditional. Conditional sentences don't go both ways. Because here we have a series that converges. We just said that a while ago. but the absolute value series diverges. That's the converse of, see, if the absolute value series converges, then the original series converges. The converse of that is if the original series converges, then the absolute value series converges. That is false. The converse of that conditional statement that I made a minute ago is false. So one way we will have to prove a series converges if it has pluses and minuses is to look at the absolute value series. If that one converges, then the original one does. But for alternating series, it's easier. You look and see, are the terms going down, do they go to zero? It's easy. Okay, so alternating series are easy to see if they converge or not. Now, the book proves the alternating series test. Again, I'm going to skip that today, but we'll probably ought to talk about it. It's kind of interesting the way it has to do with grouping the terms. So let me just say one quick thing about that. You see, if this is going down and you put parentheses around things like this, if this is smaller than this, then a new series is all positive terms. Right? But if instead of that, if I group them this way instead, you're going to find out something different happens. And so I recommend to you that you read page 773, where the author proves the alternating series test, and he brings up the idea of grouping them. Now, grouping things and removing parentheses turns out to be a harder topic. But as long as we only group a finite sum, not the whole thing, but just the S of n's, we can group them or ungroup them any way we please. So you can play with the S of n's by adding parentheses or subtracting or getting rid of parentheses. Okay? And that's what the thing on 773 is about. And I recommend it to you because you can understand it. It's not hard. It's just playing little games with parentheses. And it's good for you, like what my mother told me with castor oil. Okay. Well, example 2 is a kind of a wild example. Maybe we did that the other day, I don't remember. But it's alternating, but the B things, the B terms. So when we know it's alternating, I'm just interested in the B terms. That's the stuff without the minus. And the B term is 3n over 4n minus 1. This is the Bn. Do these terms go to 0? As n gets big, these go to 3/4. So the series diverges if it's alternating. The terms have to go down and they have to go to 0. They have to do two things. Well, I don't know if these are getting smaller or not. That's not my problem. I mean, I can figure it out. But they don't go to 0, so that's all I need. Okay? So you're going to have problems in WebAssign and in a test maybe that ask you if something converges or diverges. And if it's alternating, it's easy to see, hopefully. Now there's another one here, example 3 is n squared over n cubed plus 1. N squared, so if instead of this stuff, it's n squared over n cubed plus 1, what you're supposed to think is, this is kind of like 1 over n. Now, if this were the A's, if this was the earlier in this chapter, and you had this problem, you can do a limit comparison test with these two to show that this series would diverge. But it's not that anymore. Now it's gone to -1, to the n plus 1 or n minus 1, n squared over n cubed plus 1. And so it's alternating. So how would you prove it converges or diverges? Well, the question is this thing now, because it's still like 1 over n, but the alternating harmonic series converges. So this one might converge if it's alternating. I mean, it does. And so you might want to compare it, but the comparison test only works for positive things. The comparison test section came before the alternating series section. Okay? Now, so we might have to test this. What's the limit of this as n goes to infinity? Well, you divide by n squared. If you do that, you get 1 over n plus 1 over n squared. What does that equal? 1 over n squared goes to 0. The n goes to infinity. 1 over infinity is 0. So that thing that failed a minute ago for this one, example 2, right now the limit does go to 0. Is a function, is f of n equal n squared over n cubed plus 1. Is that a decreasing function? Because if it is, then this series will converge, the alternating one. Well, so I don't know, you look in the book, and he changes it to x. Now, why does he change it to x? Because one way to show something's decreasing if it's a real valued function is to show the derivative is negative. So, I don't want to do it, but if I make f of x equal to x squared over x cubed plus 1 and take the derivative, that means use a quotient rule. If that derivative is negative, then this satisfies the criteria for the alternating series test and the series converges. Okay. What if the derivative is positive? Then we can't use the alternating series test to show anything. It said under certain senses it is convergent. It didn't say when it's divergent. Okay. Okay. So the other thing that's in the section is very interesting. I mean, not interesting, very important for people. Because earlier in other series, we estimated the error, remember? How much is the error? That's the remainder part. That's, if you add the first 10 terms, how good are you in terms of using that number? Well, you got terms 11 through infinity that you're leaving out. How big of a mistake is that? That's the question. For alternating series, it's kind of cool. All you got to do is look at the next one that you leave off. In other words, if I add the first 10 things up and I see what I get, how far is that number off of the whole sum? And the answer is, it's on page 775. The answer is, well, if I learn about Sn, okay, how far off is that answer from the sum S? And the answer is Bn plus 1. So if I say 1 minus a half plus a third minus a fourth, and I stop there, how far off is that approximation to, how far off is it from the actual answer? Because this one has an answer, it's the alternating harmonic series. We said over here, it converges. So this one converges if I keep going forever. That's not what we do, of course. We take limit of sequence partial sums. We've learned that right now. Hope don't add up it into a number. Seems like we do, but we don't. So what's 1/2? I don't know what this is. 1 minus a half is a half. 1/2 minus a fourth is a fourth. A fourth plus a third is 7/12. That's my, if I say, I want to know how big this is forever, and I'm going to stop with 4, I get the answer of 7/12. How bad is it? How far off is the actual answer? The actual answer is 0.2 at most off. So if 7/12 plus or minus 2/10, the actual answer is in that interval. The error you make when you stop is not bigger than the next one. The next one is 1/5, that's 0.2. So figuring the error in a alternating series is easy. Okay. Now, well, I'll wait a little bit for what I was going to say next. Anyway, this allows us to estimate some stuff pretty fast, because it turns out that a lot of series are alternating. And for series that are alternating, we get quick error bounds. So what you're going to have in the exercises is, suppose I want an error of less than 1/100th when I add these up. I want an error that's smaller than that. How many terms do I have to add to guarantee that? Well, if I want an error of at most 1/100, I'd have to add the first 99. If I add up the first 99, I'll be within 1/100th of the correct answer. So that's stating the error and asking you how many terms. Another thing you do is add up the terms and see how far off you are by looking at the next one. And that's section 5. That's it. What's section 6? It gets better and better all the time, because we get more and more methods to use to find out whether something converges or not. Okay, so what's section 6? Well, its name is absolute convergence. Aha, we already did that. What's absolute convergence? You take an original series, you say, okay, there it is. You take a new one by putting absolute value around the old one. New series. This is the absolute value series of the original, which is not different if the original was all positive terms. Okay, well, that's the title. So definition 777. A series AN is called absolutely convergent if the series of absolute values is convergent. I hope that makes sense now. Series of absolute values means put absolute values around all the original terms. Okay. So they give you the alternating harmonic series? No, they give you the alternating P series. So let me write that down. What if I look at -1, I'm going to do what the author does, n minus 1 over n squared. Now, what's the alternating series? It's not tough. Just get rid of the minuses. Okay. So the alternating P series and the P series is the absolute value series of this alternating series. This P series we know converges or diverges. Converges because the P is 2. If the P is bigger than 1, this series converges. So we have an example of a series whose absolute values converge. What about the original series? Converge or diverge? Alternating series test says this one converges. But I told you a while ago that if this one converges, that one does. So now we have a second way to do alternating series. If the absolute value series converges, then so does the original. And that comes up on page 778. If the absolute value series is convergent, in other words, if a series is absolutely convergent, then the original series is convergent. Now, the alternating harmonic series is convergent, but the harmonic series is divergent. So we say the alternating harmonic series is conditionally convergent. So if a series converges, but its absolute value series diverges, we say the original series is conditionally convergent. If the original series is replaced by the absolute value series and the absolute value series is convergent, we say the original series is absolutely convergent. So we have two new terms. We have a series, it converges or diverges. We know that already. Sometimes it will be called absolutely convergent, and sometimes it will be called conditionally convergent. So on the next test in series, when we do a series test, you'll be given some series and asked, are they absolutely convergent, conditionally convergent, convergent, or divergent? And maybe more than one answer is correct. Okay, so that's a biggie from page 778. Two things, a definition of conditionally convergent, and two, a new way to test things. So now, because we're getting more stuff, we have a little more complicated deals. So suppose I take the problem the book gives us. Suppose I take the series cosine of n over n squared. Cosine of n over n squared. By the time you guys get this stuff done, you should have done several hundred series. You ought to look for places to sum series and play with them, because the test will have a bunch of them on there. If you remember the integral test, some of you will remember it very well, because you just took it or maybe haven't taken it yet. It has several integrals. The series test will have several series, maybe 20 of them, maybe 10 of them, whatever. You don't want to spend 6 hours on each one. You want to spend 2 minutes on each one. But you need to have seen them first. By the way, that reminds me about something. At the end of the hour last time, I was jumped by one of my students after we turned off the recording about my inability to add to get to 640. And I, of course, cowered down and gave in and said, I'm a bad person. So anyway, the 640 is correct. And I will later explain that, but I wanted to just say that. I didn't make a mistake. I made a mistake by thinking I could be wrong. Anyway, we'll get back to that later, but I just thought I'd point out that I got mugged the other day, and now I know it was not correct. Anyway, if I have the cosine of n over n squared, what do we know about it? Well, not much, except the cosine. If you let, is the cosine of 1, the cosine of 2, the cosine of 3, the cosines every once in a while negative and every once in a while positive, right? Because the numbers, if they get an angle in the second or third quadrant, not the fourth quadrant, right? Second or third quadrant, the cosine is negative, yes? So if the 2 radians or 3 radians or 4 radians or 5 radians or 6, if one of them gets into the second or third quadrant, we have negative numbers. But it doesn't happen all the time. Sometimes yes, sometimes no. So sometimes the cosine is positive and sometimes it's negative. That's not always. That's a mess. Okay? We don't have a name for that, but that's a mess. So I don't know what to do now. Okay? But, aha, new section. We know we can do this. I can put absolute values around the thing. Now it's all positives. Now, with all positives, I have comparison tests with all positives or non-negatives. And the following is true. Is the absolute value of the cosine is always less than or equal to 1. So these things are less than or equal to these things. And the things I got my finger on now make up a p-series. The p-series converges, so the absolute value series converges, so the original series converges. That's putting together several things we learned today. And a comparison test we learned the other day. So you see something you don't like, maybe put absolute values around it, maybe that'll help. Because once it has absolute values around it, then we have more tests. We can use a comparison test. And this is example 3 on page 778, right before a very powerful test called the ratio test. Now, let's review a bit. What I just do to show this series cosine n over n squared converges. First of all, I changed the absolute value because I just learned that. And then I compared it. But I had to have a second series to compare with that I knew the answer to already. So that comparison test, or the limit comparison test that we had last week, you have to have a second series you know about to use those tests to find out whether a given series is convergent or divergent. And maybe we don't know a comparison test or series. The ratio test is cool, and also the root test, which we'll have in a little bit, is cool because you don't need two series. So if you have a series AK, K from 1 to infinity, and maybe some positive terms, maybe some negative terms, I don't know. Okay, what we do is we look at the n plus first term over the nth term. Now, in absolute value, which we could do by looking at the absolute value series and just taking the quotients. But anyway, and we take a limit of this. So no second series involved, just one series. You grab, you have a name here, you grab the n plus first one, you grab the nth one, and you divide. Then you take a limit. If this limit exists, call it L, and is less than 1, then the original series converges. This is on page 779. Except that's not what we say. What we say is, it was true, but it's not what we say. We say the original series is absolutely convergent, which means it's convergent. But it means both the series and the absolute value series both converge. So it's a powerful test. We have this series. We don't have to do this one. We have this series. You take this test, if the limit of the quotient is less than 1, then the original series is absolutely convergent, which means that this one is convergent as well. If the limit is greater than 1, the series diverges. And if the limit is 1, you punt. That's a football thing. If the series is 1, the test fails, meaning you don't know. Means try something else. So to show convergence, you want to show the limit of the ratio of the n plus first term over the nth term in absolute value converges to a number less than 1 or greater than 1 for divergence. If it equals 1, you say, well, that test didn't work, so you don't know yet. And there's a proof, but today I'm just talking about stuff. And on 2 pages later, because we have a couple examples, 2 pages later, we have the root test. And the root test says, because they're very similar, but you use them on different series. The root test says, take the nth root of the absolute value of the nth term. Take the nth root of the absolute value of the nth term. If that limit is less than 1, the series converges, absolutely. If it's greater than 1, it diverges. If it equals 1, you punt. Now, so, for example, and I'm going to write down a couple of things here. I'm going to write down 2n plus 3, 3n plus 2. Here's a series. And I'm going to write down another one, which is minus 1 to n cubed 3 to the n. Okay, got 2 series here. This one and this one. We're in the ratio and root test section. So it makes sense that I would try to use the ratio test or the root test on these series. Which one do you think you use the root test on, and which one do you think you use the ratio test on? Well, this one is powers. The a sub n is a thing to the nth power. What's the nth root of a thing to the nth power? What the nth root and the nth power wipe each other out. So this is a prime candidate for the root test. Okay? Would this be a prime candidate for the root test? I want the nth root of n cubed over 3 to the n. Well, the 3 to the n might be a candidate for, but the n cubed to 3 to the n, that's n to the 3 over n. I'm not sure I like that one. Do you understand? I might use the root test on this one, but it's worse. The root test on this one's easy. It's just these things here. This one, no. What about the ratio test on this one? That's the ratio of n plus 1 cubed. Now, I put absolute value here because you need to, but just a minute, I'm going to get rid of it. What did I do just automatically here? I got minuses here, but I just left them off. Once I leave them off, I don't have to have these absolute values there. I don't want you to forget absolute values. But just naturally here, when you look at these numbers, you're looking at the positive ones. Now, what do you do with this? You make a fraction. This is n plus 1 cubed times 3 to the n over 3 to the n plus 1 times n cubed. Because I just took this one and flipped it. Now, when I look at this, this becomes n plus 1 over n cubed, and this is 3 to the n over 3 to the n is over 3. So this becomes 1 plus 1 over n cubed over 3. what happens is n goes to infinity. And by the way, we're not summing this, we're taking a limit. Not adding this up, we're taking a limit. The limit of this goes to 1/3. 1/3 is less than 1. Therefore, this series converges absolutely, which means it converges. This one will converge if the nth root is less than 1. What happens to 2n plus 3 over 3n plus 2? That term converges to 2/3. That's less than 1, so this one converges. And that's section 6. Okay, then there's one more thing, but we're getting out of time, and that's rearrangements. And that turns out to be we could spend a month on rearrangements. Okay, so, and I'm trying to get to stuff because I want to get to section 7. I'll talk about rearrangements tomorrow. Section 7, finally, after all that, is strategy for testing series. In other words, I've been kind of going through today, giving you some more tests. That's it. That's all the tests we're going to have. Now, that doesn't mean it's all the tests out there. I can give you about 10 more tests if you want them. Maybe I can bring a couple of series to show you that we can't use any of these tests on it. So there were famous people, people with names on tests, Rab's test and Tauber's test and Dirichlet's test. Anyway, there's several tests out there that work on series for which the ones we've just had don't work. They can't tell you anything. Okay. There's also something we need to talk about is there's a difference between the ratio test and the root test. Sometimes one of them works when the other one doesn't work, and you got to figure out which one. In other words, which one do you try first? And if it doesn't work, you still have one to try. Or if you try the other one first, if one of them fails, both of them fails. We ought to talk about that as well. It's 18 after now or 19. Anyway, there's a section 7, strategy. So this is a kind of a summary of everything, all the tests up to now. So I wanted to get to that because we're going to spend some time on series. Okay, but these are all the tests. What tests are there? There was a divergence test. There were 2 comparison tests. If it's alternating, there was an alternating series test. Then there were ratio or absolutely convergent business. Then there's ratio test and root test. That's it. Okay. So when you look at the end of section 7, it will have a bunch of series exercises, 38 of them. And that's a nice section because you don't know which test to try. When you're in the root test section, you probably try the root test. When you're in section 7, you don't know. So I want to tell you about it because you need to do lots of series. Section 8 changes the subject completely. So the first section is about sequences. Sections 2 through 7 are various convergence and divergence tests for series of numbers. And section 8 and on the rest of the chapter, I think it's through 11, that's about something new called power series. It's bringing functions, series of functions instead of series of numbers. So the good news is that we have a couple of weeks left and we only have 2 or 3 sections left before we finish what's normally in the class. And so we have some time to review. We may have some time to do some other things. We may have some time to do some of the stuff I didn't take time to do earlier. I don't know. We may just not have class. I'm joking now. You guys all of a sudden got happy. I'm not supposed to be happy. So I'm going to quit when I talk about nonsense like